Hi everyone. So now we're going to be talking about selection sort versus merge sort. So we're going to talk about the way that we can look at their big O's and thus be able to figure out which one is more efficient. Now just to give you a quick refresher, selection sort is the sort where we essentially keep finding the largest element, then putting it at the very back. And thus, every time we find the largest element and put it at the back, we know that we put it in its sorted place. So the next time we try to find the largest, we don't have to look at all the elements, we look at one less element. So the first time we look at n elements, then we look at n minus 1, so on and so forth. Merge sort is the one where we split the list into small blocks of size 1, and then keep merging them together into larger and larger lists. So first the lists of 1 get merged to list of 2, lists of 2 get merged into lists of 4, lists of 4 get merged into lists of 8, so on and so forth until we get to a list of size n, where n is the number of elements. Now here are some interesting links and stuff where you can learn about sorting. This is a Wikipedia page. This is the XSort lab that we saw earlier. This is some code that we wrote, and these are some other things. So you can go check that out on your own time. Now the interesting part is now we're going to talk about how we can analyze and prove mathematically what the big O of each of these sorts is. So the first one we're going to look at is selection sort. Now in order to understand selection sort, you have to understand this. So let's go over here. So we have a list of size 1, n elements, right? So what we do is, actually let's say we have D, C, B, A. So what we do is we find the max element and then we put it at the back. So we have A, let's say C, B, A, D. See, D was the largest, so we put it at the back. Now the next time we only look through 3 elements. So now we have B, A, and we put C and D at the back. Then the next time we only look at 2 elements, so we get A, B, C, D, and finally we look at only 1 element. So in this way, we are essentially, also we have to understand that because there's n elements, and we have to find the max n times, there's n passes. So now let's think about the amount of work we do at each pass. So the first time we do n work, then we do n minus 1 work to find the max. Then we do n minus 2 work to find the max. And then we do some more, and then finally, on the third to last pass, we do 3 work, because there's 3 elements which we haven't sorted yet. Then there's 2 elements we haven't sorted, then there's 1. So this is the amount of work we have to do overall if we add all of those numbers together, which as you notice is actually just 1 plus 2 plus 3 up till n. So it's the sum of the numbers from 1 to n. Now it turns out that this total is actually a really nice formula. And I'm not going to tell you the formula because it's better to know why than rather the formula. So let's think about it like this. We want to add up the numbers from 1 to n. So how about we add it like this? Let's add the first and last elements. So what's 1 plus n? Well, that's equal to n plus 1. Then we add the second to last, which is 2, and then this one. So 2 plus n minus 1, which is equal to n plus 1 again. Then we do 3 plus n minus 2, which is equal to n plus 1 again. So it actually turns out that we could do this all day, and it would always be equal to n plus 1. So now the question is, how many pairs of elements are there? And the answer to that is n over 2. So there's n over 2 pairs that equal n plus 1. So it's actually equal to n divided by 2 times n plus 1. And so this is actually equal to n squared. It was actually 1/2 n squared plus 1/2 n. So we go to the notes. We see 1 plus 2 plus blah 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 is equal to n times n plus 1 over 2, which is big O of n squared. Thus, the big O of selection sort mathematically is n squared. Because remember, we get this, but we don't care about constants. So then, that's how we could prove that the big O of selection sort is n squared. We have n comparisons. At each level, we do first n comparisons, then we do n minus 1, n minus 2, down to 1. We add those all together, we get O of n squared. Now let's talk about merge sort. Now for merge sort, it's easier to think, instead of adding up the number of comparisons, let's think about it like this. The amount of work at each pass, and then the amount of passes. Because remember, the big O is the number of passes times the amount of work. So here we can see that the amount of work we do at each pass is actually n, because each element gets compared at least once. So as it says here, we actually do 3n work, where we do n comparisons, then we copy it down, then we copy it back. So that's n work overall. So the amount of work we do at each pass is n. Now the question next is, how many passes are there? So the way that I like to think about it is, we're starting out at sorted lists of size 1. So we start out with lists of size 1. Then we get to 2, then we get to 4, 8, 16, 32. Now, this is the size of the sorted list at that point. So the question is, when do I get to a sorted list which is of size grid n? So basically what we're doing is we keep doubling the size of the sorted list until the sorted list is size n. So if we want to figure out the number of passes, we have to know, how many times do I multiply by 2 to get to n? Well, of course, this is just equal to log base 2 of n. So the number of passes is log of n. If you want to understand more about why it's log of n, think about it like this. Remember that exponents is the opposite of log. So if I multiplied 2 times log 2 to the log n, I would get n. And thus log n is the number of times I multiply 2 to get to n. Thus, the number of passes is log n, the number of work at each pass is n, and so it's O of n log n. Thus, n log n is the big O of Mergesort. Now it turns out that n log n is actually the best we can do, and thus you should understand just how much faster Mergesort is than Selectionsort. To put it into perspective, Selectionsort is n squared, which means that, let's say that n was equal to 1 million. So n squared is equal to about 1, or actually it's actually equal to 1 trillion. Yeah, it's equal to 1 trillion. However, n times log n is equal to, so well, it's 1 million times, what's log base 2 of a million? Well, it turns out that that's only 20. So this is equal to 20 million. So the big O of Selectionsort would lead to 1 trillion operations, but Mergesort would only do 20 million operations. That's how powerful the log n is when compared to n. So thus, we can prove mathematically that Mergesort is much faster. So this was looking at how we can prove the big O of sorts. This is something which is a big topic in computer science, and something that you have to be really good at, explaining why the big O is what it is. Of course, for this course, 112, we do it at a very basic explanation level. However, in later courses, and online, you can find much more rigorous proofs mathematically.